category of the opposite diagram. Now this more or less the way we define colimit, right? We define colimit as we take this limit over everything opposite and then with addition opposite, meaning that we take this in the opposite category. So now we apply the theorem that we already proved to pull out the limit. So we have limit over the I opposite. I opposite, what's left is C opposite X D opposite of I, right? And finally we go back from the opposite category to the category C and write limit C now D of I X, which is precisely what we need. So main representable functor is an example functor that preserves limits or colimits depending what version you consider, contravariant version or covariant version. Or maybe the other way around. If you fix the first argument, this is contravariant version, and if you fix the second argument, this is contravariant version. Okay. So another corollary from this very simple theorem. Suppose now we have the situation of two adjoint functors. I have functor f from category C to the category D. I have functor g going into the other direction. I assume that f is left adjoint to the right adjoint functor g. So then, under these assumptions, f preserves colimits and G preserves limits. So this simple observation that I'm going to prove in a minute is the reason why you can say, for example, that sometimes you consider functor and I can ask you compute the right adjoint or show that the right adjoint doesn't exist. Well, for example, if you want to show that the right adjoint G doesn't exist, for example, you can try to show that F doesn't preserve colimits. That would be an abstraction for the existence. So this is a typical application of this thing. Yeah, and there is also a short name for these statements. For the first statement, sometimes people something like RAPL, right adjoint preserve limits, just for shortness, and for the second statement is that the left adjoint preserve colimits. So just an abbreviation for these two statements. And it's used quite often in the category theory. Okay, the proof again is F is the, oh yeah, thank you, yeah. So F is the left adjoint, thank you. F is the left adjoint and the G is the right adjoint. Well, left adjoint preserve colimit and right adjoint preserve limit. Okay, yeah, the proof is formal, just a sequence of elementary computations. You look at the home between object C and the G that is applied to some limit. So the first thing, well, you use the adjunction. You write this as a home in the category D from the object f of C to the limit. Right, so then the next step, of course, is just take this limit from the first argument and write this as a limit before we take the home. So this is limit over I, now home in the category D between f of C and the D of I. So next, keep the limit outside the home and move the f as a left adjoint back to the right. So the first argument now is C and we have G applied to the D of I. So finally, again, use this theorem to write this as a C. The first object is the same C, so you take this limit and move it back into the home. So limit over I of the composition G and D. Okay, so we have this sequence of isomorphisms, and now I want to conclude that by looking at this sequence of isomorphisms, I indeed have what I want. So G of the limit is isomorphic to the limit of the composition G and D. So how I can conclude that this sequence of isomorphisms give me this implication? Just of course note that this is for any C. For any object in the category C. Well, the correct definition is still here, but let's forget about the correct definition. Can we just at least conclude that there is an isomorphism between the objects? That's a simple question. I already asked you this question, I think, at least a couple of times. Yeah. Ioannidis' lemma give us that we have this isomorphism. So this is by Ioannidis' lemma. So to be completely precise, you also need to check that the cones are preserved, but you can see that all these isomorphisms that I use are actually natural. So it's very easy to believe that the cones are preserved, and if you don't believe it, check it. So this is by Ioannidis' lemma, and so I proved only one statement. I proved the statement for the functor G, but the proof for the functor F is more or less the same, just the same computation. Similarly, F preserves the colimits. Okay, so now I want to look at several examples. So the first example is the adjunction from the algebra, where you have so let R and S be rings, and B is an RS bimodule. So R is acting on the left and S is acting on the right. So is RS bimodule. Then we have the adjunction between the tensor product and the home. So tensor product with the B is the left adjoint to the home over R, where the first argument is bimodule B. Well, we discussed, I think, with a lot of details this example when we discussed adjoint functors. Now, what the previous corollary, this LAPC and RAPO, tell us about this adjunction for this pair of functors? Well, for example, if I take the tensor product with B, right now this is left adjoint, so it's supposed to preserve colimits, right? And as an example of colimits, we can take direct sums. So the first observation is that we see that the tensor product, if you apply this to a direct sum, say some modules, which I'm again going to call di, this is the same thing as the direct sum of the tensor products. Not just the elementary observation applied to a very special kind of colimits, which is a direct sums. Well, if you know tensor products, you probably know this statement when you have finite sums. Right, so, but here, just from the general theory, you automatically get this for any sums parameterized by any set. So this is the first elementary observation. Now another observation would be, well, we know that, yeah, I didn't say this explicitly, but we prove this for the limits. We know that the limit can be always presented as the equalizer between two products, goes such theorem. If you go to the opposite category, of course, any colimit can be presented as a co-equalizer for the coproducts. So essentially, you can study separately preservation of the equalizers and preservations of the products, right? If the functor preserves both, then preserves all the limits. Now I'm kind of separately studying preservation. Here I have colimits, preservation of the coproducts, which are direct sums in the category of modules. Now the second condition to check to get something non-trivial is to study the preservation of the co-kernels. So tensor product with a bimodule B with the co-kernel of some map, so m to the n. So this is preserved. So I can write that this is isomorphic to the co-kernel of the tensor product B and M to the tensor product of the B and N. And by the way, all the tensor products, of course, here are taken over the S. So this is preservation of the co-kernel. And do you know this statement about the tensor product and co-kernels? There is another way to formulate exactly the same result. So you have M, N, and say there is L, which is a co-kernel. Right? So you can say that you have this, so this is F, and this is co-kernel of F. So you have this sequence of the modules and the maps, and the sequence is exact on the right. This is precisely what it means that, well, if I say this is exact on the right, it means that I have a map, and the co-kernel of the map is this last object. So this is something from homological algebra. We're going to study this with more details in the second half of the semester. But here we can notice that for such diagram, if I take a tensor product with B, I'll get new diagram. And this new diagram is still exact, right? This is exactly the preservation of the co-kernel. So what we proved is that the tensor product with any bimodule is exact on the right. It preserves the diagrams which are exact on the right. So if you look at some algebra textbooks, or for example, Atiya MacDonald and commutative algebra, this statement requires a separate proof. But from the point of view of category theory, well, it's just an example of an adjunction and the general properties that the left adjoint functors preserve colimits. In this case, just co-kernels. And you can do this for the right adjoint functor, which is in this case just home. Now let me just say briefly that for example, the following is true. If you take a home from a bimodule to a product of some family of modules, this is isomorphic to a product of homes, that you'll get for free, and you have the exactness of the home on the left, or in other words, home is preserving kernels. So this is the kernel. Which, if you just draw the similar diagrams, you have a map between two modules. There is a kernel, so it will be exact on the other side, on the left, and this exactness on the left is preserved by applying home with a fixed first argument. Okay. This is the first example. Now for the second example, I can notice that the colimit, when we discussed colimits for a fixed category I, that was the left adjoint functor for the functor delta, and the limit was the right adjoint functor for the functor delta. So we always have such adjunction. And since colimits, say take colimit, colimit is left adjoint, and they're supposed to preserve colimits. So then automatically we'll get something like this. The colimit I, colimit J for some category D is the same thing as the colimit J, colimit I to the same diagram D. So you can commute colimits with colimits automatically. And the same you can do for the limits. So colimits always commute with colimits, and limits always commute with the limits. This is just by the adjunction. But of course the question, can you commute colimit and the limit? This is completely different kind of question and requires some additional proofs. Sometimes this is true for some special diagrams, but it's not true in general. Okay. So now I want to prove the following theorem. There is kind of another relation between the limits and functors. So any functor f on any category C to the sets is a colimit of representable functors. This is a general theme in the category theory when you apply this to something, for example, for modules. You can prove, for example, that say a module is a colimit of special kinds of modules. For example, any module is a colimit of finitely presented modules. Then if you know that your functor is preserving colimits, for example, it's enough to prove a statement for this functor about the finitely presented modules. Then you automatically get the statement for any kind of modules. So there are very many statements in the algebra of this form, and this is just an example of such statement in the category theory. But now in this case, the category we're interested in is just the category of all functors from the category C to the category of sets. To prove this, right, so I want to show that the functor f, say f, is the colimit over I of some diagram D. So the first question is, what I need to choose to write such colimit? Well, let me take as an I the opposite category of the category of elements of the functor f. So of course D in this case is just the corresponding diagram. C sets. So these are elements of the functor f. I'm going to define this category right now. So I'm just saying that first of all I'm choosing this category I to write this colimit. Elements of the functor. It will be explained in a second. So in this category, so in in the category L of f, the objects are just formal pairs. So pairs of the object C and the point X. So in this case, C is just an object in the given category, and X, well, is just you apply functor f, you get some set, and you choose in this set a point. So this is the second element in the pair. So you can see why this is called the category of elements. It's like you just consider all the elements kind of in the functor for any given argument C. So that's the category of elements. Well, that's the objects in the category of elements. Of course, there are also maps. So the maps, so if you want to have a map, say f from the pair C and X to another pair C prime and X prime, well, that's very easy to define. It's just a map f from the C to the C prime, which is just a map in the category C. And there is an additional requirement that if you apply your functor to this map little f and compute this on the element X, you're supposed to get element X prime. So that's the definition of this category of elements. Well, as an exercise, you can notice that you can actually present this category of elements as one of the examples of the comma category, but we don't need this for the proof. Okay. Now, what's the diagram D that I have in this picture? So the D on the pair C and X, this is by definition, again, I start defining my functor on the objects. So this is just the representable functor H sub C. So you can notice that this doesn't depend on the element X. And if I have a map F from C to the C prime, well, then the D of this map, this is what I'm going to call, for shortness of the notation, call F with the upper star. And this is just the induced map of the functors, so the induced natural transformation. I have HC prime to the HC, and this is given by the F upper star. You can notice here that I switched the order. It was mapped from the C to the C prime. Now this is kind of from the HC C prime to the HC. So this is why I need to write opposite here for the category I, because the functor D that I consider is actually contravariant. Okay. Okay. Now another thing to notice maybe is the following. If I have a point little x in the f of c, well, by the Ioannidis lemma, I can interpret this f of c as the natural transformations from the functor h sub c to the functor f. Right? So this is by Ioannidis, and it means that actually taking a point in this set is precisely the same thing as considering a natural transformation. So I have the following triangle, so H sub C, F upper star H C prime, so this is just a map, and there is F somewhere, and there are corresponding maps, which are natural transformations. So some of the things I suppose are clear. For example, I think it's clear that if I have as a category I, this category of elements, it is clear that I have such maps, right? Because I'm just using the Ioannidis lemma. Maybe what is not clear at the moment is why the square is commutative. Sorry, not square, triangle. So why the triangle is commutative? the condition that triangle is commutative is actually already written on the blackboard in another form.
We do it like that. I mean, f from f x.
Yeah, so you say you essentially, well, this is the interpretation of some data in terms of the natural transformations. It's by this kind of dictionary provided by Ioannidis lemma, right? So I'm now using the right-hand side. But if you go by Ioannidis lemma to the left-hand side, you still get some condition which is equivalent to the condition that this triangle is commutative, and that's precisely this condition. So let's maybe check this with more details. So I have a natural transformation from the h sub c to the f. By Ioannidis lemma, I know that I can identify this with the f of c. I have the same, but for the c prime. So natural transformations from the h sub c prime to the f. By Ioannidis lemma, I can identify this with the f of the c prime. So now here I have f functor f applied to the map little f. And here, well, I have just the natural transformations induced by the f upper star with a fixed argument, with a fixed second argument, which is just a functor f. And this f upper star is just natural transformation, which is induced here. Okay, so now you can notice exactly that by looking at this square, you can notice that the condition that, for example, you apply f upper star, which is you go along this arrow to the x, which is just you identify this natural transformation with the point x here, is the same thing as the just, well, taking the point x and applying f of the little f to the x, which is again the x prime. So okay, the commutativity of this plus this condition give you exactly the condition that this triangle is commutative. Okay. But the meaning that this triangle is commutative is precisely that if you look at the diagram h sub c map to the f by some little x, so now this little x, which is the second argument in the category of elements, is just kind of the projection in the cone, right? So we have this cone over the diagram, which is the diagram over the category I, which is the opposite category to the category of elements. To say that this is a cone, we need precisely to check that this condition is satisfied, that all the such triangles are commutative. So this is a cone. Now the last question is, which we need to check, is that this is a limiting cone. Okay, so let's take this cone and let's take another cone. So we have f h sub c, so there is f upper star h sub c prime, so x prime, and suppose we have another cone, say with the vertex t, and I'm also going to call the corresponding maps little t. So what we need to show is that there is unique natural transformation theta such that all these triangles are commutative. Right, that's exactly the condition. This is a limiting cone. Right, so the initial object in the category of cones. T? T is another cone. So so we have this huge diagram which is parameterized by elements of the category of the elements of the functor f. I'm just drawing kind of just one arrow from this diagram, but you can notice that this arrow, there is such arrow for any C, F, and C prime. And for any such arrow, there is the corresponding triangle, which is commutative. And all this data together, they form a cone with the vertex f. So I'm just drawing one arrow in the diagram and one square, but you can imagine that there are plenty of such things. And the same is true for any cone, right? With any vertex t. So I'm taking my cone, which is kind of I just constructed before with the vertex f, and I take any other cone with the vertex t, and again with the same conditions that all the corresponding triangles are commutative, because that's the definition of a cone. Now I want to check that my cone with the vertex f is in fact a limiting cone, which is by definition means that I need to show that there is a unique natural transformation from this f, functor f, to any functor t. If I can do this, well, that's essentially the end of the proof, right? That would be exactly the colimit. Well, but we need a natural transformation. So if I want to specify natural transformation, I need to specify all its components. So for example, I want to specify a component for a given object C of this natural transformation. All right, and what are the options, essentially, how I can choose this natural transformation? Notice that now for a given object C, this has to be just a map of sets. Can you guess what the map of sets is? There are not so many choices here. Well, yeah, essentially, well, in your category I, right, you have pairs object C and the element which we can interpret as a natural transformation. So here the C is fixed. So the element that we interpret as natural transformation for first diagram is X, and for the second diagram this is T. So essentially the only possibility to write a formula here is just that X is mapped to the T. So let's take this as a definition of the natural transformation. And then we need to check that this is indeed a natural transformation. So we need to check the commutativity of the square. So f of C, theta sub C, T of C, f of the C prime, theta C prime, T C prime. So this is G F. So this is the condition that we need to check, but we can do this computation explicitly. So let's start with the T of F, which is composed with the theta sub x, which is applied to some element little x. Well, since we know that we can write this as it's just essentially the same thing as the T of F, which is applied to the theta sub C of x, right? And we know that this is just the T of F by computing this thing is T of F of the T. But the definition of how we define this component of natural transformation. So, but this thing is just T prime. And on the other hand, I can also write this T prime as the theta sub C prime of the x prime. Right? This is still T prime. And I can write this as this theta sub C prime of the f of the little f of the x. So which is the composition of another two maps on this diagram. So this composition. So if you take this composition and you take this composition, the answer is the same, which is T prime for any given element x in the f of C. So indeed, that's a natural transformation. So that's the end of the proof. Okay. So my next goal is to formulate and prove maybe some of the versions of the special adjoint functor theorem and general adjoint functor theorem. And to do this, I need the notion of generators and cogenerators. So let's briefly discuss generators. And cogenerators. Okay, definition. A set of objects, say, let's call this Gi, parameterized by some set large I. So set of objects in a category C is called a set of generators, or another terminology, a generating set. That's the same thing. If we have the following property, so if for any two maps, F and G, which are different, so F is not equal to G, so these are elements in the home set of the category, say from the object X to the object Y. So for any such pair, we can find a map H, which is in the home set in the category C from some Gi to the X. So there is a corresponding index. Maybe I need to write this into as a two conditions, or that there is index little I in the set I, and there is map H from the, say this is in the home set, from the Gi to the X, such that if you take precomposition with the map H, you still get some two different maps. So such that F precomposition with H is different from the G precomposition with H. So that's a definition of a generating set, and I can formulate as a second sentence an object G in the category C is called the generator. It's called the generator if the set that just consists of this one object is a generating set. So remarks. So first remark about the terminology. So generators in the old literature are also called separators. And I guess we can see the reason why they call separators from the definition. It's maybe if you compare this with the generating sets from the algebra, where you generate a group or algebra or something like this, separators has a little bit more sense. So then the second remark, which is more or less follows immediately from the definition of faithful functor. So this family Gi is a set of generators, or generating set. So is a generating set if and only if we look at the corresponding functor, which is the product of all representable functors for all the objects gi, so take the product over I, and this is a functor from the category C to the category of sets, so this is faithful. So apply the definition of faithful functor in this case, and you precisely get this condition that you have in the definition. And finally, not to repeat the definition, or maybe I can formulate this a little bit separately, say definition prime of the cogenerators. So a set, now let's call this Qi. So the set of objects is called a set of cogenerators if Qi opposite is a set of generators. So it's just a short way to formulate this definition, but what it means is you more or less have the same condition, but instead of taking precomposition with the H, you take postcomposition with the H, just inverse the order of the arrows. Okay, that's a formal definition. Maybe to make sense out of this definition, let's look at several examples of generators and cogenerators, and we'll look at more such examples on the seminar. Examples. So as usual, we start with the example of sets. So in the category of sets. So can you tell me a generator in the category of sets? Yeah, the point is fine. But how about the set with two elements? It also works. So essentially any set which is not empty works. So any U which is not an empty set is a generator. So in this case, this whole set of generators consists of only one object, and yeah, I think it's very easy to see that this is true, right? So if you have at least one point, right? If you have two different maps of the sets, they don't agree at least on one point. You just take precomposition with this embedding or any. So that's a generator anyway. How about the cogenerators in the category of sets? Sure. Well, like in this example, any non-empty set is a generator. You have plenty of non-empty sets. So this is, in no way this is canonical. Yeah, but how about the cogenerators in the category of sets? What set we can take as a cogenerator?
Any but not all elements.
Hmm?
Any two or more elements.
Yeah, that works. So any, say, set Q such that in the Q there are at least two elements is a cogenerator. Oh, this is what I wanted to ask. Do you have a reason why you need at least 2 points?
Because you want to put different points with similar value.
Yeah, that's true. But well, that's the reason why the set with 1 point doesn't work, right? But what if you have two points in the queue? Why this works?
Because we have passenger different, so we can 2 points which are different from each.
Mm-hmm.
So we can send one point.
Yeah. That's the reason. So you see that this is exercise a little bit too easy for the seminar. Now in the example number 2, I'm not so sure that this is easy. So let's take abelian groups, and what are the generators in the category of abelian groups? So can you give me an example of a generator? What?
Maybe 3 abelian groups.
Well, can you be more specific? Maybe just choose one. Yeah. So that's a good example of a generator. But of course you're right. So you can raise this set to some power and get any free abelian group, and it's still a generator. And in general that would be true. Even more would be true. If you have a generator, you can add to this generator anything. This is still a generator, right? In the category of abelian groups. But why, for example, integers is a generator in the category of abelian groups? So the question was why this is a generator. So I suppose when you say that any free abelian group works, you had some reasons.
So we send two f, ну, f уже различается в какой-то точке, и вероятно мы отправляем что-то не единицы из этого точки. Не понятно, что типа такое.
Well, you don't really use that as a group homomorphisms if you say something like this. I don't know, maybe there are different explanations, but for example, you can use this remark about the faithful functor, right? But if you take this as an object, what was the remark? Yeah, so the remark number 2, right? If you take the corresponding object, so there is no product, there is only h sub z, right? So this is just the home with the first argument z is fixed. But what is this functor? This is just more or less the identity functor. You take an abelian group, right? And you interpret this abelian group as a set or forgetful functor. So clearly this is a faithful functor. So this would be one of the explanations for example, h sub z, which is just the home in the category of abelian groups, right? Is forgetful functor. Forgetful functor. So it is faithful. Okay, so example number 3. Let's take the category of all groups, not necessarily abelian. Well, more or less the same reasoning is. Yeah, but I forgot about the code generator. Let's first discuss the code generator. Well, the code generator, I think it might be a tricky question, It's maybe something that we want to discuss later when we discuss homological algebra, but I'm just giving an answer right now for you that you can take the Q modulo Z, and this is as an element in the category of, as an object in the category of abelian groups, is a cogenerator. Now in example 3, we look at all groups, and you can use more or less the same reasoning to show that the integers is a generator. But what is the cogenerator in this category? Okay, any guesses what's a cogenerator? Hmm? No. Free group on two elements? No. Well, the question is interesting because the answer, there are no cogenerators. So that's the first example of a category where we don't have a cogenerator. Oh, you can go to the opposite category and you get the category without a generator. So, but why there is no cogenerator? That's not a trivial question. So maybe we'll do this on the seminar, maybe today, maybe next time. Okay, so let's take a break. direct limit of the symmetric groups.
What should the answer look like?
Now we already know the answer. Just all the permutations of the natural numbers such that this permutation is identity up to find how many non-trivial elements. Or only find how many elements this is a non-trivial permutation.
Yes.
Do we have a solution?
And we should prove it.
Hmm?
And we need to prove it. Or
Yeah, we need to prove that the answer is what I just described.
you just can't try.
So yeah, I want to show that this is something. Right. And for this, I need let me call this group no G. I need to show right, and then I'm done. Okay, I can erase this, yeah. So say we have our group H, and we need to we have morphisms, sort of Fn from Sn to H, and they are all compatible, and we want to construct Fn. Изоморфизм должен быть такой естественный, это равносильно, это определение копии дела. Ну да. Ну, я не буду этим особо пользоваться, это я просто записал то, что я хочу сказать, что это такой предел просто. And I want to construct such factorization. Okay. It's better. I have f here, so it will be fine. So we have f. Say that n is such that f does not permute anything that is larger than n. Yes? Then I could say that f lies in Sn if we embed it as a subgroup of G. Right? So then, well, I need to construct such phi, and I.
Maybe you want this capital N. F is not the
Yes, yes, yes. You're right. You're right. Then I defined phi of f as phi n grade of f. I need to show what? I need to show that actually it is well defined. It is homomorphism because phi n are homomorphisms. So I need to show that for any different such n1 and n2 we are good, right? And then we are done. Actually, I didn't really need it because I could just take the minimal, but okay. Let me, for the sake of just saying anything, say that, let's say that n1 and n2 are such that they both satisfy the condition we need. Yes. And without loss of generality, let us have it n1 is lesser or equal than n2. Then we have this embedding. And since this diagram is commutative, we are done, right? I'm not actually saying anything. I mean, I guess once we define it, it's more or less obvious, then it's all right. I would be happy to answer any questions. I'm not sure if I could prove anything here. Okay, have I convinced anyone? Seems that neither.
No, maybe just you can just repeat the argument. Maybe it will cause some questions.
Okay, so I take this group G of permutations of natural numbers that are just identity starting after some fixed some natural number. Say I have okay, and then I want to say that the image naturally Sn are embedded into G, and they form a filtration on it. Okay? So then I say, all right, take any element of G. Since Sn form a full filtration on G, they lie in some Sn, actually starting from some fixed n. And then take any such Sn and just apply the maps where we were given. And that's it. And by the definition of a cocone on the diagram, it will be well defined. And since all of them are homomorphisms, it will be homomorphism. I guess that's it.
Second example of the direct limit that we saw in the lecture was the following. You take such directed set of abelian groups and you need to show that the direct limit is isomorphic to the proof group for the prime number p, which, if you want, you can consider that this is defined as the localization of p of this modulo z.
So at first I want to define co-projections from this group to proof group. It will be find
So what's this symbol? F what?
FKT. So it sends 1 to 1 over p to a power k. So it is group homomorphisms.
So why is this group homomorphism?
So we can just check what, and so like this.
Yeah, I think what we need to say that this is a group with one generator.
Yes.
We define homomorphism generator.
Mm. So it is clear what is, or it is group homomorphism, or I need to check this.
No, I just explained. This is the cyclic group, right?
Yes.
If you want to define homomorphism from a cyclic group, it's enough to define this.
Yeah, I defined it on a generator, so I just. Now we need to check that we have some abelian group and co-projections from all with. And so on. And I need to prove that we have unique co-projection from proof group so how I will define with morphisms, I want to define it like this.
Is it really a valid notation? I noticed that I saw anything like this.
Что?
One exists and unique. Okay, this is the other way around.
Oh, yes. I will define phi by this way. So we just need to check what all commutes and what is it is group homomorphism. So I think it's clear what if L and M is co-prime with P. I think it's clear that it goes to because with coprojection is group homomorphism.
How do you use exactly what is co-prime L and M?
Yes, with P.
With P.
Yes.
Why do we need this here?
Вообще, наверное, это не нужно. Нам нужно проверить, что если я буду домножать числительно π, то все будет хорошо. I think I can erase this. check that now M is co-prime with I need to check with is by definition, and with is by definition but what's this? It is just f of f of oh no, сейчас. So we know that with commutes so because of this triangle is commutative, we'll get what with equal to this. Потому что у нас вот это должно коммутировать. So we checked that multiplication by p to some natural power does not affect on what we got, and so.
I don't think it's a good idea to erase properties.
Yeah. And so if we have something like this, now we just can find a common denominator. So it goes to and because of commutativity of same triangle, but there's no L and N, but M and D, we have this thing like and our properties checking the same way. Like if we multiply some я лучше тоже напишу. So we multiplied our number by some of our number, and I wrote it like with number is coprime with p, and with is the maximal power of p. So I want to check that it's but that is we know that multiplication by p doesn't affect on a morphism, and we get so we checked that it is group homomorphism, and we need to check that it commutes with all and that it is unique. It commutes with all, so it commutes with all arrows because we define it like this, and we need to check that I can. Okay. And we have co-projection to proof a group. And we have co-projection to our group. And we need to check what all these triangle commutes, but we are also commutative because we defined phi like with way. So yeah, we just defined that and by definition, so all these triangles are commutative, and we checked that a triangle like this are commutative. Why it's unique? So I think it follows from that if exists such morphisms, it should be commutative on all these diagrams and on all of these diagrams. So we have some our morphisms or morphism. We just will see that it's defined by the same rule. Ну, вот у нас есть какой-то гомоморфизм из группы в прюфе в нашу, и мы знаем, что если этот треугольник коммутативный, то он согласован на каждом элементе. И мы просто пишем это в обратную сторону, получается. То, что это на каком-то элементе должен быть равен на этом же элементе. Ну, для любых, да, для любых там двух групп и для любой группы тут, да.
So let's prove one general property of the limits. So there are situations where limits are very easy to compute. So suppose you want to find a limit and you know that there is, say, I naught, which is the initial object. So then in this case, such limit is just the value of the functor d on the initial object. It's an easy exercise.
Начальный объект какой категории мы следуем?
Yeah.
Начальный объект.
Какой вопрос?
Что имеется в виду во второй строчке?
Что его начальный объект?
Категории А.
Но больше нет.
Okay, so I is initial object, so we can one morphism from the I0 to the okay. We have only one morphism in image of I, so and identity morphism from the I0 to the I0. So the I0 is cone over our diagram.
I think what you can say is that there is only one arrow from I0 to any
From
I, right? And then to this map you want to apply D.
yeah.
But you cannot say that there is only one map from di0 to the di. It's
Uh,
not true.
There is one map in image of I.
From the image of I,
Um,
what it means.
Okay. Okay. There's one image from I0 to I. So there is
So the I0 and the f for every I is a cone over this diagram.
Why?
Why not?
Well, for all we have a precise condition, right? We need to know that
Yeah.
all the triangles.
Okay. We need to show that 0. We need to show that the triangle is commutative.
We already used that of this.
Okay.
Maybe something not used.
Maybe two. Okay. So there is a commutative diagram. This. So I think this is commutative too, because there is only one morphism here and here. So this is a cone over our diagram. Why this cone is limit? Because for every other cone we have only one morphism.
Yeah, we need to explain why this is exactly the case. So suppose you have another cone, right, with some vertex. Why there is only one map to this vertex?
Only one. Okay.
And why there is a map? That's also a question. Or you need to show that there is a map, right?
А почему для I0 существует стрелка всегда?
М?
Почему для какая стрелка всегда существует для I0?
Ну, потому что у нас I0 это инициальный объект, и из него ровно одна стрелка в любую ишку в I.
Мы сейчас универсально будем доказывать.
Ну да, нам надо доказать, что только одна стрелка такая есть в него. I need to prove that there is only one map. Yeah? Okay. If we have
No, so you need to show that there is at least one, right?
T is a cone over this diagram. So we have maps from T to every this element.
But it has to be I0.
Yeah. Okay. If we have two maps from T to D I0, so Ага. Ну, пусть будет H.
И тогда другая выпускается через тождественное D0 всегда так. И что
В смысле?
это, конечно, может быть. Как?
Сейчас.
Ну, просто нарисуем
Сейчас, да.
D0 как отдельный конус, и тогда будет удобно. Просто ты
Окей, сейчас. Я понял. Okay. If the diagram is commutative. Ой, сейчас. Yeah. There is H is a composition from ID and G. So there is only one H.
What's that? I think there is still something missing. Why there is only one H?
So if we had two morphisms H and J, that this diagram is commutative. We have this is H, this is J, and this diagram is commutative. But H is composition from ID and J. G.
I still don't see what argument you're making. You're just saying the answer.
Это называется аффирмация.
Ну,
у
нас, да, у нас.
D0 это конус над самой этой
Ну да, у нас
Вот.
есть два морфизма, такие, что диаграмма коммутирует, и мы просто говорим, что вот один из них.
Морфизмы вершин конуса.
Ну да.
Вот. Одну из стрелок мы берем из конуса T.
Ну да, то есть у нас вот это H как стрелка из конуса T над диаграммой, а вот это G как морфизм между вершинами конуса. И у нас вот это D и 0 вот тут как конус над этой диаграммой с ID, вот это T вот тут как конус над этой диаграммой с морфизмом H, а G тут как морфизм конусов. И он должен коммутировать совсем. Поэтому у нас получается что как раз вот просто композиция, что композиция G и ID это H. Я пытался сказать то же самое, но на английском. У меня не получилось.
Okay, thank you. And by the way, of course, you can notice that there is an opposite statement with the elements and the final objects. It's just the same thing for the opposite categories. So the next question is to show that in a category with equalizers, well, this just means that in this category any pair of maps, parallel maps, has an equalizer. Any idempotent splits. So that's the statement, and let me, for the safety, repeat what the condition that any idempotent splits means. Now you have, say, object X in the category C. We have a map P from map X to the X. So this is idempotent, meaning that the P squared is the same as P. So idempotent P splits means that I can find another object Y. I can factor this idempotent P from X to X, which is mapped from X to X, as the composition of the two maps f and g. So P is equal to the GF. And also, if I take the composition in the other order, take first G and then apply F, this is the identity on the object Y. So this is the condition that P splits.
So assume we have an object X and the map P to itself, which is idempotent. Let's take an equalizer of the P and identity map to the X, and let's call this map G. So we know for any other object, for example, X itself, with a map P, which makes this diagram commute because P is idempotent. We have an arrow F, which is P with composition with G. So we have to check that, so we know that GF equals P. We want to check that FG is identity on E. Well, if we take E and take the map FG, then this is GFG, and we know that GF is P, and well, we need to check that PG, but this triangle commutes, but it's easy to see because P squared is P. And so yeah, we have only map from E to E, which is identity, so it is FG.
From a category which is just a group, but they consider the category with one object, and find the corresponding limit.
First category is category of divs.
No, the category is just one group,
Ah,
and they consider this as a category with one single object.
Okay, so in this case our diagram is just a single object, but it has a lot of arrows going from itself to itself, which correspond to elements of the group G. In total, we can view like this functor as a set X with an action of G. Okay, so what is a con over this diagram?
Yeah, I think it's an important thing to understand that this functor x is precisely the same thing as the set of the G action.
Yeah, it's the set X equipped with the morphisms, the images of this functor under this functor of the elements of G. Yeah. Okay, so what is the con over this diagram? It means we have like X with, once again, the actions of G. Let me write it like G1, G2, G3, etc. And we have some element L, no, or maybe element Y. To give a functor from the category G to the category of sets is the same data as to give an action of the group G on the set X, where X is the image of the unique object from this category. So the con over this diagram is a set Y and a single map from Y to X, which commutes with all the actions of G in the following sense. Let me call this map Y, or call this map F. We have F like Y goes to F at Y, but here we can apply the action of G to get G F at Y. And here we again have the same map F. So this is precisely the property that the map F constitutes a cone over this diagram, and it means that F at Y is an element such that for every G in G, we have G F at Y equals F at Y. It just means that the image of the map F lies in the stabilizer of the action of G on X. Okay?
Stabilizer. Is this the right word? Or invariant element?
Okay, maybe invariant elements would be, yeah, okay. Stabilizer is the other way around, yeah. So it means that con is the same as F such that im F lies in invariant elements, okay? So now how to construct the limiting cone. I assert that the limiting cone is just this set itself, xg, and the map just id, in the sense that I send invariant element to itself, but okay, canonical embedding of this set of invariants into the set X, which just sends each element to itself, but viewed as an element of X. Indeed, how to construct the unique map from every cone to this one? Okay, we have to like give, let me call this F tilde. We have to define F tilde for every Y in Y, and I define it to be equal to F at Y. Once again, this is the unique way to define this way such that this triangle commutes, and this map is well defined because F at Y, as we have seen, lies in the set of invariants of the action. So, and naturality is obvious, tralala.
problem just a little bit. So if you didn't come up with this solution, this is your second chance. Compute the co-limit of the same thing. Do you want to solve it? Maybe we can wait another 5 minutes.
So what does Kakon look like? It is also some object with property. If we go from U to U prime, or go from U to by some action of a group and also to prime, we'll get same answer. So it may be written like this. And it is for all, and this property is for objects from O. So now I wanted to construct.
The way it's written is G1, right? It looks like this is condition just for G1. Maybe you can write just G and say that this is for change G1.
Yeah, yes. So I'll take this binary relation of equivalence. And I'll take x factorized by this binary relation of equivalence. So we how?
You call this set U, right?
Yes.
And now
Oh, with element. Ну, я запутался немного, к сожалению.
But for elements, this is fine.
I think clear that and I think what
Want to check this in equivalence relation?
ну надо проверять. Ну ладно, тогда окей. So I just need to check if I have some U prime U and with I need find the unique map from U prime to factorize by equivalence relation.
Usually this is called the space topology.
Yes. Yeah. So it's a canonical projection. So how I will define f? No, just. Надо только сказать, как я U получил.
Yeah, and I think you also want an arrow in the other direction.
Что?
You want an arrow in the other direction.
Да, это правда. Ну да, окей.
Which now makes a lot more sense.
Угу. So I need to check whether this well defined, but it is well defined because for all U prime, this property are hot, and because of this property well defined, why it is unique? Because if we have some theta from U factorized by with equivalence relation to U prime, and with triangle is commutative, so it is clear what theta may should be defined like that.
Next question is to find the limit of the representable functor. Sorry, no. Not the limit, co-limit. Let's find the co-limit of the representable functor.
Потому что у тебя, если у тебя есть такая стрелка из полуфакторизованного в', то по коммутативности этого треугольника на каждом классе эквивалентности она должна быть определена в одном месте. Но класс эквивалентности на самом деле это образ элемента из двух проекций канонических.
So long as вы совершенно реальная вещь происходит, у вас есть функция, которая постоянная на орбитах, да, действует уже, ну, понятно, что она единственным образом может быть рассмотрена как функция на пространстве орбит. Вот от того, какую точку на орбите взяли, ничего не зависит, просто надо понимать, какое значение эта функция принимает на любой точке во всех орбитах.
А x это просто какой-то объект категории
Yeah, any object. What is surprising that you can actually compute this co-limit and give an explicit answer.
То есть и это просто какая-то категория, да?
Да.
А x какой-то объект.
Да. Сегодня тоже не успеем разобрать, давайте это отложим на следующий раз. Но может над этим подумать, у этой задачи есть всякие занятные, очень короткие решения. Ну, такие, не совсем прямые.